Welcome back. If you have ever looked at a state space model of a control system with all those matrices A, B, C, D, it can feel a bit overwhelming, like a complex machine without a manual. It's easy to get lost in the equations, but a real understanding comes from seeing the underlying geometry, how these matrices actually shape what the system can and cannot do. It's not just about numbers. So today we are going to cut through that complexity and look inside the machine. To do that, we will dive into two of the most fundamental concepts from linear algebra that tell us almost everything about system behavior: range space and null space. Last time we discussed linear operators and state that a linear operator is a linear map that map vector from the domain vector space to the codomain or range vector space. Such a map satisfies the property of additivity and homogeneity, which together define the linearity condition. We also mentioned that every linear operator can be represented by a matrix once bases of the vectors of the domain and codomain space are specified. Conversely, any n by n matrices with entries in the complex field can be regarded as a linear operator that maps the vector space Cn into the Cm. Alright, so right here for our control system, the state equation tells us how the internal state, which we call x of t, change over time. And output equation, that's what we can actually observe or measure. Think of it like reading a voltage from a voltmeter or the position from a GPS sensor. But the real magic, the brain of the system, is packed inside those four matrices A, B, C, and D. We have got our state vector xt living in an n-dimensional space Rn. Our input vector ut lives in Rr, and our output vector yt lives in Rm. Now, each of these matrices has a job, a geometric role. A governs the internal dynamic, how the state changes by itself. B shows how the input influences the state. C determines what we actually see, mapping the state to the output. And D gives the direct fit through, connecting the input straight to the output. So when we look at all of these together, the state space model is really a set of linear operators, matrices A, B, C, and D, that map between different vector space. In other words, the whole system is a composition of linear maps, and understanding those mapping, that geometry, is what lets us truly see how the system behaves. Let's think for a moment about the mathematical limitation of the model. The model that's supposed to describe the behavior of a real-world machine. I'm not talking about numerical solution or simulation accuracy. What I mean are the boundaries, the mathematical limits built into the model itself. Every complex system, whether it's a self-driving car or a power grid or a robotic arm, cannot just move or behave in any way that's theoretically possible. Its evolution is restricted by some hidden mathematical boundaries, a kind of hidden geometry behind the equation. And that's our mission today, to find those geometric boundaries. When we model a system, mechanical, electrical, whatever the domain, we describe it through matrices, these linear operators A, B, C, D. Let's call them collectively M. Now think of M as a filter. It defines how an input passes through and becomes an output, how it translates into a result into the system's behavior. And here is the fundamental insight. That every moment you define a system using this operator, these matrices, you have already defined its boundaries. In other words, the rules themselves create the limits. So the big question is that, does the system's state or output trajectory truly span the entire theoretical space available to it? Or is it limited to a much smaller specific subspace? And here is the key idea. The subspace is defined purely by the structure of those matrices A, B, C, and D. That is the geometrical core of system behavior. It tells us what the system can physically do, and just as importantly, what it cannot do. Let's start with our first concept, the range space. Take a generic matrix M. How do we define the set of all things it can actually produce? All the reachable outputs. The definition is simple. The range space of M is the set of all possible vectors Z in Cm that can be written as a Z equal M times X for some X in Cn. If such an X exists for a given Z, then Z is inside the range space. If not, it's outside. Think of it like a restaurant menu. Every restaurant uses ingredients from the same grocery store, but each has its own menu, its own set of dishes it can actually produce. That's the range space, the set of outputs a matrix can cook up. Now let's bring this idea back to our control system. In the state space model, the equation x dot equal a of t x of t plus bt ut define how the state vector change over time. Here a times x and b times u together form the velocity, the instantaneous direction of motion in state space. And this is where the concept of range space become physically profound. The range space of A and B represent the directions of motion the system is allowed to move in. It defines what combinations of internal dynamic from A and external commands throughout B can actually generate movement. So if you try to design a controller to move the system in a direction that lies outside the combination range space of A and B, you are essentially fighting the system's inherent geometry. It literally cannot go that way. In other words, the range space defines the boundary of what is physically possible. So if range space represents all possible changes, all the outputs the system can produce, then what about inputs that produce no change at all? The ones that lead to zero outputs. That brings us to the complementary concept, the null space. The null space of a matrix M is the set of all vectors x in Cn that when multiplied by m produce absolutely nothing. Mx is equal 0. If the range space is everything the machine can produce, the null space is its geometric blind spot, the set of input that system simply doesn't see. The key idea is this: vector in a null space are invisible to the operator M. If you feed the system an input that happened to align perfectly with the null space of the M, it gets completely absorbed, producing no effect at the output. It's silent. To make it concrete, imagine designing a flight control system. If a pilot commands an input, but that input happens to lie in the null space of B, aircraft won't respond at all. It's like pushing in a direction the system doesn't even recognize. So the null space represents those hidden directions, the dimension that a particular matrix ignores. It's the opposite of the range space, which define the direction that can generate change. Together, these two spaces, range and null space, define the inherent structure of the system's potential and its fundamental limitation. They form the geometry of what the system can and cannot do. Now, the power of understanding range and null space really comes alive when we apply them to a specific control scenario. Our source material shows that these geometric concepts don't just have a theory. They directly govern how real system behave. Let's look at two key examples. Example 1 is about the frozen state. Imagine your system is operating normally, and at a specific moment in time, let's call it tau, the state vector x of tau happens to lie perfectly in the null space of matrix A. Remember, A governs the system's internal dynamic, how it evolves on its own without external input. By definition, if A of tau, x of tau is equal 0, then the internal term that defines the system's evolution vanishes. So the state equation x dot of tau is equal A of tau x of tau plus B of tau u of tau reduced to x dot of tau equal B of tau u of tau. This means the system internal motion freezes. It only moves if there is external input u of tau acting throughout B of tau. But there is another geometric layer here. Even if u of tau exists, the system will change only if that input lies outside the null space of B of tau. If u of tau happens to lie inside the null space of B of tau, the input energy is completely absorbed. It pushes again the system's inherent geometry and nothing happens. So being in the null space of internal dynamic or state equation physically means no influence, no effect, no motion. For the second example, we want to discuss about the idea of input decoupling. Suppose you intentionally choose or the system naturally process an input signal that always lie in the null space of d of t. That means d of t u of t is equal 0. Then the output equation simplifies beautifully to y of t is equal c of t x of t. Physically, this means that direct pass from input to output is eliminated. The input has no immediate effect on the measured output. As a control designer, this can be extremely useful. You can apply certain control command through B to shape or adjust the internal state x of t without directly disturbing the output y of t. This effectively decouples the input from the output, allowing you to use system's internal geometry to achieve control object more delicately. These examples show the range and null space are not just mathematical abstraction. They dictate system behaviors, and understanding them provide a deep geometric foundation for control design strategies. Up to now, we have seen how the null space and the range space play a crucial role in identifying both the behavior and potential of a system, and how understanding this geometric structure is essential for designing effective and optimal control strategies. From this point onward, our goal is to find methods that help us characterize these two sets more precisely. We are calling them spaces, but we haven't yet shown that they actually are vector spaces. In fact, both are ended subspaces, but of different vector spaces. A range set of M is a subspace of codomain, and null set of M is subspace of the domain. The proof of these statements is quite straightforward. In general, if you want to show that a set S is a subspace of a p-dimensional vector space defined over C, you need to verify two conditions. The first condition is every element of S also belong to CP. That is, if Y in S, then Y in CP. It means S is a subset of CP. And the second condition is the set must satisfy closure under addition and scalar multiplication, or equivalently satisfy the linearity condition. For both range and null space, the first condition is obvious from their definition. Elements of range space are outputs of M, so they belong to codomain Cm, and element of null space are inputs of M, so they belong to domain Cn. The second condition, linearity, is automatically satisfied because M itself a linear operator and satisfy linearity condition. Thus, both range and null space are subspaces. Each is defined by geometry of M, and each of them are subspaces of different vector space. Null space is subspace of domain, and range space is subspace of codomain. Once we have proved that the range space and null space are ended subspaces, it naturally follows that each of them must have a basis and a well-defined dimension. Let's start with the range space. Its definition is quite straightforward. The dimension of the range space is simply the number of linearly independent columns in the matrix M. This comes directly from how the range space is formed. When you multiply a vector x in Cn by a matrix M, you are taking a linear combination of the column of M. Therefore, the range space is exactly the space spanned by column of M. From basic linear algebra principle, the dimension of any spaces spanned by a set of vectors is equal to the maximum number of linearly independent vectors in that set. In matrix theory, the maximum number of the linearly independent column of a matrix is called the rank of the matrix. Then the dimension of range space is equal rank of M. It's also proven that the number of linearly independent columns equal the number of linearly independent rows. So we can equivalently define rank in both ways. So if dimension of range space is R, it should be less than or equal minimum of dimension of domain and codomain of matrix M. Hence, any collection of R linearly independent column of M form a valid basis for the range space of M. For a square matrix, M is said to be full rank if its rank equals its dimension. That is, if all of its rows and column are linearly independent. In this case, determinant of M is not equal 0. If the determinant equals 0, the matrix loses rank and its range space has lower dimension. Now it's time to define dimension of null space. We call this the nullity of matrix M. Let's assume the nullity of M is K. Since the null space is subspace of C of N, there exists K linearly independent vectors in Cn that span the null space of M. Because Cn is itself an n-dimensional vector space, we can also define additional set of n minus k linearly independent vectors, w1, w2 to wn minus k, that complete the basis of Cn. For each vi, we have mvi is equal to 0. Now let's see what happens when m operate on these vectors wi. For each wi, mwi is a non-zero, and resulting vectors mw1, mw2 to mwn minus chi are linearly independent and together spans the range space of M. Therefore, the dimension of this complementary subspace, the part of Cn that is not in the null space, is exactly the dimension of the range space. This leads us directly to the rank nullity theorem that says the dimension of the null space is dimension of the domain of M minus the rank of M. Intuitively, the rank tells us how many independent direction in Cn are mapped to non-zero outputs, the visible direction. The nullity tells us how many independent direction are flattened to 0, the invisible direction. Together, they describe how the linear operators M partition the geometry of its domain into parts that influence the output and parts that are completely silent. Thank you.